Okay, so a long time ago in a galaxy far away, all of the matter in the universe was created in one specific moment called the Big Bang. So everything was at a singular point, and then this massive expansion happened where all of this matter expanded throughout the universe. And in general, what happened is it just created a bunch of hydrogen. Okay, with maybe some heavier metals and stuff, but it was really just it was just this just random matter that began to coalesce into protons and neutrons and electrons, and the simplest form of it was hydrogen. And the hydrogen, in any kind of process like this, it created a general even distribution throughout the universe of all the hydrogen, but it wasn't perfect. And because it wasn't evenly spread throughout, there were little concentrations here and there. The general effect was that when you had a slight concentration of a few more hydrogens here than in other places, that when you had a concentration of the matter, it would start to coalesce. So as we had this random distribution of hydrogen, there were some places where there was a little bit more hydrogen than others. And when that happens, it created more matter. And that matter created a place that was more dense than other places, which led to a higher gravitational field in that area, which started to suck in more hydrogen. And so instead of having just this universe that was just even distributions throughout the universe of our matter, back when our universe was much smaller than what it is right now, because the universe is constantly expanding, but we'll get to that a little bit later. Instead of it looking like this, we started getting little pockets. Where hydrogen would just start collecting in little clumps. And these clumps started to attract other clumps. Okay? And we had what was called an accretion, that all of these clumps of hydrogen started getting bigger and bigger and bigger as they sucked up more of the hydrogen. Just the gravitational pull of each of these clumps would start pulling into each other. It was very, very weak, but there was nothing else opposing it. Not like yesterday where we looked at the protons and electrons where they're, where they'd be attracted to each other, but if there's an electron on the other side, then it would be repulsive to each other. Gravity doesn't do that. Gravity is attractive. There is no negative gravity. There's no gravity that pushes against. Everything is attractive. And it's just because you have mass. Well, eventually these clumps got to be really, really big. And when they got to a particular size, okay, we'll just draw it like this for right now. When they got to a particular size, the cumulative gravity of the hydrogen was enough, or exerted enough, it exerted enough pressure on the center of the gas to cause fusion at the center of this massive ball of hydrogen. And that fusion, nuclear reaction, combining of hydrogen atoms together, it exploded, and that's the birth of a star. That it created a star when it fused all this hydrogen.
What is the second word saying?
Cumulative. Okay. This is the birth of a star. This is how stars happen. It is the force of gravity it's the force of gravity of all this mass pushing onto each other, attracting itself. But at the center, there was enough gravity, and enough force on the very center, those central atoms, for them to fuse, for their nuclei to join each other, for, if you remember from last semester, the for that to happen, He. But then this would start fusing with other things, and mind you, that's not a normal helium. But this is what would happen. Most of the hydrogen was like this. There would be 2 1s and 3 1s, making 3 2 and 4 2 helium. And creating a star, and when it erupted, it began to emit massive amounts of light. The energy that it gave off was in radiation and light leaving the star. Yes, Brenda. Enough. Yes. This process happened for billion, and is still happening for billions and billions of years. In fact, this will go until it runs out of fuel. Our sun is one of these. Our sun is a plain old, ordinary, run-of-the-mill, main sequence star. It's just boring. We have a plain, boring star. It's not too big, not that small. It's just kind of meh, average. And it's running out of fuel. It's been burning for about probably 5 billion years, maybe a little longer. And it's expected to run out in about 5 billion years. And when it does so, it's going to start to expand. Because the fusion, the energy released due to the fusion, or actually the mass fusion is going to be expelled, and so it's the fuel that's given out there is going to spread out, and it's going to create what's called a red giant. And if we have the sun, yes, I'm making it green. Deal with it. It's really white. It is our sky that makes it look like it's not. And so we have Mercury and Venus, and we're looking at it from on end because my circles are terrible. Earth, Mars, a region where there's a whole bunch of asteroids, and then out here we have Jupiter. Okay, so Mars, Venus, Earth. I'm sorry, Mercury, Venus, Earth, Mars. And then all this asteroid belt. Okay, the red giant will expand to include the orbit of Mars. Okay, and it'll get really cool. It'll get much cooler, but a whole lot bigger. Now, mind you, we're talking 5 billion years from now. Long time. We don't have to worry about that. We're not going to watch it happen. Long time from now. But this is okay. Then it will eventually, all of that will slough off, and it'll eventually shrink down to the size of maybe Texas, maybe a little smaller, and it will become a black dwarf. A black dwarf? DWA. God dang it. Okay. Okay. It'll shrink down to a black dwarf, and it'll collapse, and all of its mass that it used to be will shrink down to something really small, smaller than the moon. Small, probably about the size of, have a diameter the size of like Texas. Okay, all of that mass, and it'll be exceedingly dense to the point where if a teaspoon of it would weigh like 100 million tons. Yeah, that dense, because all the space of an atom would just be collapsed into solid matter, and that's okay. So that is the life cycle of the star. Now, how can we tell all of this happens? Oh. Well, we can look at it. And as we gaze out into the universe, we see all these different we can see all these different stars in various sizes and various shapes and various stages of their life. And how can we tell what stages they're in? Okay. Or even how far away they are? How do we know that the universe is as big as it really is? It is not the Illuminati. Rex.
Satellites?
What about satellites?
Well, they can take pictures of it, and so you can get like an idea of how big the universe should be.
But if we just take a picture of it, how can we tell for scale? How do we know how far away the little pinprick is? Anthony.
If you think about like how big our like solar system is,
Uh-huh.
and like you use like that scale, and then you bring it out to like how many stars there are and compare it to our sun, you can kind of get an idea of like how big it is.
That's probably the beginning of realization of just how big the universe is. Let's think of it like this. Did you know light from our sun takes 8 minutes and 20 seconds to reach Earth? Okay, mind you, yes, this is lecture. This you do need to know all of this. No, the sun is continually shining, so it and has been for quite some time. So the light traveling from the sun hasn't stopped showing up here. We've always had light shining on the Earth. It just, if any one particular photon of light leaving the surface of the sun takes 8 minutes and 20 seconds to get here, if it travels at the speed of light. Or in other words, we are 8 minutes, we are 8 1/3 light minutes from the sun. You guys follow that? Okay, because a light year, a light minute is a unit of distance. It's not a unit of time. And so, if the sun were to all of a sudden go out, we wouldn't know about it for 8.5 minutes. It won't. It's not a possibility unless you wait for 5 billion years. Okay. But if through some supernatural process the sun were to blink out of existence, we wouldn't know it for 8 minutes. Okay. No, how do we know how big the universe is and how far away things are? Well, that brings us to something called the Doppler effect. Okay. And here's the Doppler effect. Anything that emits waves, or a signal of some kind, does it with a certain frequency. So, I wish I had. You may or may not be a fan, but have you ever seen a video of a car race?
Yes.
Okay. And now they have these cameras where you can sit inside, or the camera's inside the cockpit of the car, right? And then they also have cameras outside. And so if you're inside the car, what does it sound like? The whole time, right? And it's just the same droning, they wear earplugs when the drivers wear earplugs when they're in their cars just because it's so loud and their engines are going. It's you can hear gradual changes as they step on the gas or ease off. What does it sound like if you're sitting at the edge of the track? Okay, you have that shot where they're coming around the curve and you have the camera looking down the track and the cars are coming and what does it sound like? Right? Why does it sound different? Why does it sound different from the person outside the car than the person inside the car? It's the same thing making the sound, right? Okay. Here's why. The Doppler effect. And here's the idea. As the source of the wave, in other words, the engine of the car, is emitting sound, it's emitting what's called a wave front at a particular frequency. Okay, so here is our sound emitter. Okay, and if you are traveling with the sound emitter, you're going to experience the frequency, the same frequency as the speaker, and it's never going to change. But if it's moving towards you, these wave fronts get closer together. So as these hit your ear, if the sound emitter is getting closer, as it's moving towards you, the wave fronts are going to be closer together. Because the sound emitter is like pushing out the wave fronts. They're still traveling through air at the same speed, but because the emitter is moving faster, or is moving towards you, those wave fronts get closer together, which sounds like an increase in the pitch, which is why when something's coming at you, it's right? And right when it's here with you, they're the same. And as it gets past you, now all of a sudden, the wave fronts get further apart because the emitter is now moving away from you. And so what this sounds like is, does that match your experience if you've seen these? Okay. This is the Doppler effect. Now I just use this with sound, and you guys see it with sound. You mainly experience it with sound. Because light moves really, really fast. But light does a Doppler effect too. So, keep that in mind for a minute, because we need to shift gears. And we need to talk about emission spectra. You guys saw yesterday the emission spectra for hydrogen, neon, and krypton. Yeah? Okay. And hydrogen, because it's easy to draw, looks like, or it looked like, so hydrogen. Okay, we had a blue like that. Uh-oh, I'm not remembering. It was a blue and then an orange. And then a red, right? It was the light. It was the turquoise, the orange, and the red, right? Wasn't that it for hydrogen? You guys remember? Yeah. Okay. Now this is if we took a sample of hydrogen gas and we sent electricity through it and we got it excited. And this is the light that the electrons would give off. But the reverse happens if you take a bunch of hydrogen and you shine light through it. If I were to shine white light, which I'm actually going to draw as black for right now because I'm drawing on a white background and you can't. If I use my white ink pen. Right. So, we're going to use black. And here is a black light source. Or, I'm sorry. It is a white light source. It is not black light. It is a white light source. I'm just drawing it black. Okay. And it gives off light. But it passes through hydrogen. These colors, okay, which we know that hydrogen will emit once we excite all the electrons, these colors are the exact same frequencies that will get absorbed if we shine white light through hydrogen. Okay, and so there's an inverse spectrum, okay, which looks like, and I don't quite have a picture prepared for it. Okay, so your hydrogen is going to give off this. And the top one here is what you guys saw yesterday in the darkened room when we sent electricity through the hydrogen. We saw the red light, the blue light. I had to make a change. It's actually blue and purple. The red light, the turquoise, and then there's, if it's kind of dark, maybe when you watch this on your computer, you can see the dark blue and the purple on there. But hydrogen will absorb those same colors. See that there's the red? There's the red, and the turquoise, and the blue, and the purple. Okay, they're a little more faint over here, but these are also absorbed by hydrogen a little bit. But those three lines and our red one over here are also absorbed when we send white light through hydrogen. Yeah? Well, we can look at, then, stars and see what colors of light have been absorbed by the gases within them. Yeah? and we can see what elements they're made in, or what elements exist in those stars. Yeah? Okay, so we have two pieces here. We can look at the absorption spectra, or the emission. This is emission spectra because this is what's giving off light. The top one's emission spectra. The bottom one is the absorption spectra because that's the light it absorbs. But they're just mirror images of each other, right? They're the same lines, just one's absorbed, one's black and so it's going away, and one is colored so it's giving off. You guys follow me there? Okay. So now we have these two pieces. We have the Doppler effect, which says that frequencies change. Frequencies change with a moving emitter, like say, a star. Okay, and we have absorption spectra. Actually, that is a P. Okay. And the absorption spectra will identify the elements that are absorbing the light. So here's what we see. We see our absorption spectra except these colors, instead of being right where they are, they're the same distance apart from each other, but they've moved over. Red's a little bit over here. Yellow's over here. This yellow screen's here. Turquoise, blue, purple. They've all shifted over towards the red end. Well, wait a second. If that's the case, okay, and we'll study this a little bit further, this means that the frequency has decreased. The frequency of the light has decreased. And if our frequency decreases, that means the things that are emitting the light are doing what? Remember what happened with the Doppler effect. What happened when the pitch of the sound decreased? The thing that was making the sound was doing what? Was it moving towards you or away from you? It was going away from you. We find this effect with every single star that we look at in the universe. And the further away it is, the larger the effect. And there's only one way that this is possible. That all of the stars are moving away from all of the other stars. And the universe itself is expanding. Okay, so, the universe is constantly getting bigger. What happens if we go backwards? Okay, right. So if we go back in time, the universe is getting smaller, right? So as we go forward in time, the universe is getting bigger. So if we go backwards in time, the universe is getting smaller. So if we go all the way back to the beginning of time, what was the universe like? Well, it was how I described at the beginning of the lecture. It was a single point. It was all of the matter was condensed into this one little tiny place. Okay, and this is the evidence that we have for the Big Bang. Okay, and with the expansion of the universe, it had to have been infinitely small at some point, and we went back in time. Okay, and there's all kinds of this light scattered throughout the universe as a result of this Big Bang.
Is it possible that scientists can pinpoint where the Big Bang happened?
Yes,
Have they done it yet?
here, and there, and there.
Whoa.
Because everything in the universe came into existence at the Big Bang. The universe itself expands. So, everything that was in existence was in this little tiny point. Okay? And existence itself expanded from that point. Everywhere is the Big Bang. Okay? All right.